Welcome back to the PAC Festival with our last speaker from the Easty Boy stage. So it's going to be Lloyd from Bon Jovi, named in the Blue Jeans app at the moment. So Lloyd is the CEO of Neocortix, and he is going to talk today about global last mile load tests with NeoLoad. In fact, Neocortix allow you to do any type of load last mile testing with any type of product. And here is going to cover that with an example with NeoLoad.
So here's a brief overview of the talk. First, I'm going to begin with just this very brief history of last mile load testing, since there has been a industry participant in this space some number of years ago that some of the old timers in the community will probably remember. Then describe this new technology, which we believe is well suited for the global last mile mobile load testing. Then the bulk of the talk is going to be case studies showing load testing with performance optimization and a number of different details. I'm going to sort of build up the case to a real user, the kind of test case that a real performance engineer would see, the way it's done with conventional data center load testing, and then with this global last mile load testing. So you can see a comparison between them. Once you see that, then there's a general optimization loop consideration that I think it's a point that can be made once you've seen the examples. And then finally, just this brief discussion about, I think we have an important potential new tool in the performance engineer's toolkit. I'd like to cast it in that light. Okay, so that's an overview of the talk. So first, the history of global last mile load testing. Senior folks in the field who have been working in this space for a decade or more may remember a company called Gomez, which was around in the early 2010s. So like 2011, there was a strong presence in the industry. I believe that they were acquired by Dynatrace, and then Dynatrace was acquired by CompuWare. I saw them when I began to enter the field in 2017, and I sort of witnessed from one week to the next as they were shutting down. So I seem to remember seeing the death of that organization inside CompuWare in 2017. So this is an example of a similar technology to what we're doing at Neocortix. There's a similar good technical idea here. What they were doing was a global network of PCs in people's homes, but they had what I think of as a flawed business model, which is something different than what we are doing. Namely, they were coupling their hardware offering, their availability of devices, with their own software that would run on it. So you ran Gomez software for load testing on the Gomez network of devices. And I believe that it was not possible to run any other tools on their network of devices. So they were a bespoke hardware, software platform. And I believe that that was a business model that doomed them to difficulty in the marketplace. What it needed to be to succeed was a general purpose cloud platform, more like AWS EC2, that ran on PCs all over the world, and that would be capable of running other load testing tools, not only their own Gomez tool. So senior folks may remember this and remember that it didn't succeed. Now Neocortix comes along with a new technology that bears some similarity to Gomez, but has important differences in those places where we think that there was an opportunity that they missed. So now we have Neocortix Cloud Services in 2021. This is a global network of Android mobile devices, not PCs, running secure Linux containers, not just dedicated software for load testing, but general purpose cloud services platform running secure Linux containers. And because it's these Linux containers, they can run any software, load testing software, network telemetry software, any flavor of load testing software, JMeter, NeoLoad, any other package that you want can run in this platform as long as it can run on Linux and is built for ARM. It has a convenient use case identical to AWS, which is what the industry is expecting and used to, with the mere advantages of being less expensive than AWS and having better geographic distribution. as shown in the map on the right side of this screen. Okay, so we have a new technology that we believe is suitable for certain kinds of tests for performance engineers. Just one more slide on sort of the properties of this solution, and then I'm going to dive right into these use case and the details and showing the data that we've collected. So the first key difference to the old Gomez thing was it needed to support many different kinds of tools. So we've spent a lot of time at Neocortex working on that. You see on the bottom left panel here, we support NeoLoad, Torus, JMeter, Locus, Gatling, K6. Dynatrace is shown here not as a load testing tool, but it's a monitoring tool that we interface to from the other load testing tools. And you also see we have Puppeteer and Lighthouse. So it's necessary to support also the individual, the browser emulators and the performance monitors to be able to have the option of measuring direct user experience, including browser effects. So that flexibility is extremely important. It didn't exist previously, and now we have that. We've also invested heavily in making an easy batch runner interface, so it's possible for any engineer, senior or junior, to be proficient quickly, just be able to set up and run a batch load test at pretty much any scale, and to be able to do that in a small number of minutes with just issuing a Python command to launch the instances and run the load test as specified in your command files. In the upper right here, we have a picture of a typical large-scale load test. It's done with about 800 devices. This is our twice daily regression test, just to make sure that our system is working well. This one happens to be based on Locust. And the certificate of completion here is just an indication of, we have dozens of engineers who have completed these certificates that attest to the fact that it's easy to use and people are able to follow the instructions and get up to speed quickly. Okay, so now let's get into the detailed use cases. I'm going to start at the very beginning with the simplest possible load test. That is a load test effectively with constant load from a nearby data center that simply tests the simplest possible server, the system under test, which simply returns a text HTML file. That's as one of the things that Scott Moore mentioned in his talk. That's the simplest possible case. That's exactly the place where we started. So let's make it so that we can do a load test, simple, constant one, and let's just test. Does everything work the way we expect there? Well, when I first ran that, this was in the early days of when I was starting to learn JMeter, I expected to get a constant response. Basically, every page should take the same amount of time to complete. I expected, because it was a data center close to the server was in Phoenix, and the data center was Amazon Oregon West, which is close in internet terms to each other, should have been about 0.7 of a second, or 0.07 of a second, 70 milliseconds. But what I got was this plot on the left. This is the scatter plot showing all the detailed responses. Like Schepper's superfood, he likes to look at the raw data, and so do I. I expected to see effectively the flat blue line at the very bottom of this graph, but what I saw was this dotted line that was above it by about 3 times the factor. Instead of 0.07, 70 milliseconds, it was 21 milliseconds approximately, and it was bursting with a 60-second period. Well, I was stumped by that, and so I put out a notice. At that time, I wasn't really on LinkedIn, but I was on Stack Overflow. I asked a question there, and one of the experts said, oh yeah, that's the secure channel setup time for HTTPS. So there's a handshake that has to take place, and that involves 3 transit times. Send the request, you send something secure back, the keys, and then send your final response. So that takes 3 passes through the transit time, but that is done once the beginning of the session in the thread on JMeter, and then there's a timeout. This HTTP client for time to live parameter, which by default in JMeter 5.3 is 60,000, which means 60,000 milliseconds or 60 seconds. And so sure enough, that parameter is what controls this little period of this dotted line. Well, when I looked at that, I said, that's not what I was expecting. And so is that right? Is that what it should be doing? Is that what a browser experience, a person who is hitting this web page in a browser, would they see every minute they would get a slow response, and then for the rest of the minute they would get faster responses as they visited other pages? So I posed the question on LinkedIn. There wasn't really a definitive answer. And my question was also, did anybody else notice this? Seems obvious that something's amiss. It appears, if I could summarize the results, that no one really has noticed this. One person said, perhaps the reason we didn't notice it is because the effect is so small. The difference between these two lines here at 0.07 and 0.21 seconds is 140 milliseconds, and that's too small for any user to notice. So we didn't notice, we wouldn't care, it's that small. And I would venture also they were looking only at mean response time and maybe 95th percentile, and that would have been just a slight blip in the 95th percentile, and the mean would hardly have changed. So there was a lot of reasons why it seems that no one had noticed it until, it was the first thing that I did, and it's the first thing that I noticed. So I took that advice from Stack Overflow and learned how to change this parameter. Turns out if you change it to HTTP client 4.time-to-live equals 1, my slide actually says 0, but if you do that, I think that sets it to the default. It just goes back to the default. But so if you set it to 1 millisecond, then you get the result that I'm showing here. And now they all take 0.21 of a second. So effectively, you've slowed them all down, but you've made them uniform. And so that result looks more realistic to me. So at the moment, I don't have a definitive answer from my colleagues, but to me, that looks better because it doesn't look right to inject into the load test results a periodic 60 hertz artifact, which is not present in anything that the load generators are doing, nor is it present in anything that the system under test is doing. Right? So it's an artifact of the test. And well, when I look at the raw data, I don't like that. So to me, I prefer the smooth predictableness of this rightward one, even if it's a little bit slower. So now that's the result looking at it from the point of view of a nearby data center, where I agree, the effects are small because everything is so close. But now I'm going to show you the first plot in the slide deck for a global last mile load test with a map like the one I'm showing in the bottom right here, where you see lots of blue points in the United States, lots of red points in Russia, and green points that are in all other countries in the world. So green means everything that's not US or Russia. And now, if you look back on the bottom left plot, you see that there is a strongly periodic response, and this one is showing it with a period of 20 seconds. Right? So you see 5 bursts in 100 seconds, and that's because I have set the parameter to be 20 seconds as the period. So that's controllable by that parameter. Now, in this plot, you can see that there's a dense set little stripes in below 0.3 of a second. There's blue at the very bottom, close to 0. There's green above that, and then there's a little band of red just at about 0.3 of a second. And you notice that in that bottom thick band, it's not periodic at all. It's just constant solid dots. But then you go above that, and what you're seeing is that periodic effect. Well, that's the result of many. In this case, it's about 50 independent instances from all over the world that are contributing all of their responses, all of which look something like the one in the upper left, with the periodic triple response and the dominant response, which is faster. But they're further away. So it's no longer going from 0.07 to 0.21. It's in some cases, in the red points, which are in Russia, it's going from 0.3 of a second to about 1 second, 0.35 of a second to 1 second. So this tripling of the delay in the handshake is no longer a small effect. It's a whole second. And the difference between the two is about 0.7 of a second. That's a big deal. That would be enough to fail a service level objective. that would result in the requirement to go back and do some further optimization. So that's what it looks like if you just use JMeter with a 20-second period in that time to live. If you change time to live to 1 millisecond, you effectively make it so that it never holds the channel open. Now you see the behavior looks different. Now you don't see that periodic response anymore, and you don't see those super fast responses either, because even the fast ones that were close to 0 have been tripled. So now the slowest ones are approximately 0.2, and there is a uniform non-periodic bursting band, just a simple straightforward band of raw data. It looks like the global last mile extension of the plot that is above it. Well behaved, smooth, no funny periodic artifacts. Now we've got a clean starting point. Now we know what things look like in a data center, and we know what things look like from a global last mile test in a simple case. Simple in the sense that the system that is under test is doing a very simple thing. It's only returning a text HTML file, just like what Scott Moore said. That's the simplest thing for that server to be doing. Now that means then that as we add load to it, because the effort is 0 to handle the requests, you can add pretty much as much load as you want, and it doesn't ever slow down. You don't ever see a catastrophic failure. In fact, you don't even see any response time increase because it's 0 effort to fulfill the request. Okay, so that's the basic starting point. Now, when Stein Scheppers saw this on LinkedIn, he said, that's weird, and that's interesting, good find, and I haven't seen that in any other tools. So do the other tools do that? Here's the plot that I returned to Stein's question, and showing that basically all of them, except for one, does the same thing. Here's JMeter again with a 20-second period. Gatling has a response, but with a much longer period. So it's approximately 360 seconds. You see this secondary burst of red and blue. So it's not many periodic hits. It's one long delay and then a big hit. K6 shows the 60-second period. Clearly, they have a default like JMeter, 60 seconds, but with a twist. You'd see that the response, those little scallops here are extremely narrow, and something strange happens that doesn't happen with JMeter. They tip as they go further to the right. So that means there is a delay-dependent shift in this this resetting of the secure channel. Quite strange. I've asked about it to people at K6, and I'm not sure if people are going to work on it or not, but there was some initial interest in investigating, taking a look and see if they could duplicate the issue. Locust has another similar effect, looks a little bit like K6, but not quite the same, and it seems to disperse over time. So basically, every one of these well-known load tools behaves differently with regard to this HTTPS secure channel setup time. Torus is the only one that behaves like my clean example from the prior slide. It looks like it's behaving with HTTP for client.time to live equals 1. So it looks clean. So that's the answer to Stein's question, what do the other tools do? Okay, so now I want to get to the case study that shows what a real engineer would see. Check time here. Okay, so we need a programmable system under test that now doesn't just return a simple text response as shown in the bottom left. It doesn't just return a simple HTML file. Now we see in the upper left, we really are delivering load. In this, not a huge amount of load here, but we're getting up to 65 hits per second. We're hitting a rather small server, but as long as we only ask it to return a simple text file, it has no trouble at all returning the files. And you see that the simple text response is completely flat. There's no additional delay with responding to that small amount of load. But now I've created a programmable system under text so that it can simulate something more like a login page. Eric Progler and many of the other senior people in the field always emphasize it's these login pages or these new account creation pages that actually do some real work. They access databases, they have to wait for responses from other machines, they do some serious crunching for a small amount of time. And so I wanted to simulate that. So in this block of code, most of it's just setting parameters. There's 4 lines of code where the action actually happens, starting with for z in range 0 to num sum loops, going down to time.sleep. So basically, it's a loop that goes 5 times. The number of subloops is 5. And in that, it repeats 5 times, do a little bit of computing, and then simulate waiting for a database on another machine to give you an answer. So crunch a bit, request something and wait 0.2 of a second, get the answer back, crunch a bit more, do 5 of these little cycles. So it's the simplest possible thing that would behave in a moderately realistic way. Now we have something that it effectively has 2 interesting parameters. You see the fact at the unloaded case, the delay shows here as about 1.2 seconds. Well, what's that coming from? This is from a nearby data center, but so that's coming from a second of delay to handle the request, and then 0.2 seconds to get to the data center. Okay, so that's the response. And then when we get up to load of about 50 requests per second, we start to see signs that it's getting into trouble. That's because the total amount of computing that it's doing with these little bursts of intense computing are starting to bog it down. And finally, when it gets up to 65 hits per second, it's now actually flailing. And so you see the complex response to this more realistic server under test condition showing the effect of load on this system under test. But this is all with just a nearby data center. Now I'm going to take this set of examples and put this into the global last mile load test situation and compare it to the data center so we can really see what it looks like. So here's another variation of that, slightly different parameters, but in this case, it gets up to a load of just over 100 requests per second. And in this case, it's still 1.2 seconds in the unloaded case. It handles 100 quite nicely, just a small amount of additional delay. And once it gets above 100, then it starts flailing. Now, in a typical regression test being done by a performance engineer, perhaps a daily load regression test, the scenario I'm going to describe is going to be one where this would pass the service level objective. The objective is that it should always respond with no more than 1.5 seconds, as long as the load is at 100 requests per second or below. So that's the green box. And as long as none of these blue points are in the green box, then it's passing the service level objective. Okay? And so this is a condition where a seasoned performance engineer would say, great, it's passing the test every day, no problem. But now I'm going to tell you something extra from this. The support team in another city is saying, but the users are complaining that it's actually slower than this. You say that it's meeting the 1.5 seconds, but they can tell that it's slower than this. The people in Singapore are saying it's too slow. It's not as fast as you say it is. Well, the test says it's good. So what could be going on? Well, I'll tell you that this is the result of using a biased measurement. And the bias is coming from the fact that the load generator is a very high performance device in a data center that is extremely close to the system under test. So this represents a best case, not a typical, not a worst case. It's the best possible case that you could possibly measure. If you measured this exact same system with the same simulated behavior, it would look like this. If you measured it with devices all over the world. Now you see our green, blue, and red points. You see this thick band, not a thin, well-behaved band because it's coming from one tight data center. This is coming from points all over the United States. The blue dots all over locations. The green dots are coming from locations not in the US and not in Russia. You notice that one of the green sets of dots looks like it's coming from inside the United States. That one is coming from Vancouver, Canada. That's outside the US, but it's close in internet space. It's not like Europe or Australia. Right? So the green dots can be mixed in with the blue ones. And then finally, you see the red ones are all a lot longer. That's because Russia, all of Russia, is pretty far away from the server under test in Phoenix. Okay, so now you get this thick band, and now if we apply the service level objectives, you see that many of the points are inside that region. That means that it is, under the global last mile test, it is correctly reporting that it is failing the service level objective. And the reason it's failing is because this is an unbiased measurement. It's actually a good representation of the true distribution of real user response times. Okay, so what that means, this is extremely important. It's not just that it's a measurement that tells you the truth about what your users are experiencing. It's telling you that optimization is needed to meet the requirement of the service level objective. And so if we do the optimization, now the way that I've done that in this case is I've tweaked the parameters of the server. I've simulated the optimization that would be done by all of these fancy SQL data manipulations and all the enhancements to the loop unrolling and all that stuff that reduce the amount of computing and reduce the amount of delays in getting those database responses back. And now if we do that, now we have an optimized response, the result of all of that optimization work that now reduces the delay under load, and it reduces the spread that occurs when load is present. And now you can see that it is now passing the service level objective. For example, 95% all points should always be below 1.5 seconds. So now we see we have an optimized system, correctly optimized, because we've done an unbiased measurement. Okay, so now this is a general principle. On the left, I'm showing a optimization loop. In its simplest basic form, you start, you measure the response times, you compare it to the service level objectives. If it's a pass, you stop. And if it's a fail, you improve the performance like we just did in that example. And then you go back and measure it again, compare again, and now you go around this loop, measuring, remeasuring, and re-improving until finally you exit with a pass, just like we did with only once through the loop and around. However, here's the key principle. If you have a biased measurement inside an optimization loop, this is a well-known phenomenon in control theory, that measurement better be unbiased. It's okay if it's noisy. Many passes, many remeasurements will wipe out the noise. But if it's consistently biased, you have a situation that will either give you instability or a hard limit catastrophic error. This is extremely important. In the load testing case, the biased estimate is caused by using only high-performance servers in nearby high-performance data centers to deliver the load and to measure the response times. The result of putting that biased measurement inside the feedback loop, the control loop, is you get a premature termination of the optimization loop because of that biased measurement. And in other words, the net result is the engineer says everything's great, and the user says, to quote Stein, help, this website is painfully slow. That's Stein's slide. That's the condition. This is the cause of that condition. Bias estimator inside a feedback loop. Now, to the question of, really, how well known is it that this is a really bad idea? Well, the Boeing 737 MAX team found out the very hard way that this is an extremely bad idea. This is the reason for 2 plane crashes, the grounding of a major Boeing airliner in the last several years. Well-known case, absolute tragedy, because of a biased sensor in a feedback loop that even when the plane was flying straight and flat, the sensor was saying, you're too high, biased upward in this case. And so the feedback loop was saying, we've got to bring it down, bring the nose down, even though the nose was already in the correct position. And so the pilots could not stop it from diving into the ground, even though it was flying straight. That's an example not of a premature termination of the optimization loop. That's an example of a failure to terminate the optimization loop. It should have said, I'm fine, pass, exit, and just keep flying straight. It refused to leave the optimization loop constantly trying to push it down. So it's the opposite sign of the effect, but it's the same effect. Let me just check on time. I think I'm maybe just a couple more minutes. I think I have just 2 more slides. So, so all of this, now I've shown working examples, show the importance of optimizing in the feedback loop correctly without a bias. The net result, there's an economic benefit to all of this. This equation was based on some early LinkedIn posts that I did. They were trying to say, well, what's the economics of performance engineering? How do we account for the costs and for the benefits of it? And how do can we make some estimate of what's the return of our investment on this? Should we spend more on, should we have more engineers or fewer? Should we have more license or pay more for software, or should we use free tools? Should we test more often with more instances? D instances, the cost of the instances. And similarly, there's these benefits, in particular, the benefit of performance, the benefit of having a fast-performing website under load. So on Black Friday, yeah, it doesn't crash, but it's still too slow compared to your competitor. So that's a benefit of having it be fast under load. The benefit of stability is having it not crash actually under load. Both of those are benefits. They're equal to the cost that would happen if the disaster occurred that you're trying to avoid and test for in advance. In this case, we can actually say what the benefits are for global last mile load testing. In this case, the first is a benefit on the cost. The costs go down because we have deliberately set the prices to be lower than AWS. I think that's unexpected. Most engineers say, well, we can't possibly do this. It's going to be more expensive than the way that I'm used to. No, it's actually cheaper. We've gone out of our way to set the prices lower, to make it interesting and attractive to try. But nope, the cost goes down when you do it with these last mile devices. The benefit of performance, I've actually shown you in the working examples. The benefit of the performance is you optimize correctly because you have an unbiased estimator inside your feedback loop, and the net result is your performance improves. Now that, not only is that just sort of, it's the whole point of being a performance engineer is to get that desired performance benefit, but if your company is in a competitive environment with another company and you do this and your competitor doesn't, he does it the old way with the data centers, and your company does it with the global last mile and truly measures the responses, then your company will improve and they will stay comfortable thinking that they're doing fine when they weren't. You'll get a performance benefit, and that increases your return on investment and improves your competitive position. Similarly, the stability effect also occurs. This is another point on the previous plot that showed that once you optimized it, I think that's actually worth going back for. Once you optimized it, take a look. The scales on this plot are different than the one on the left, the middle and the left. You see that this one lasts all the way up to the 4th step in the load, but that 4th step is not at 100, it's at 130. So the optimization not only made it faster for the users, but it increased the load at which failure would occur. So it improved Black Friday. It could handle more load because of the good optimization that was done by the engineering team. Okay, so you get all those benefits. Now, finally, this is my last slide, a final positioning on the merits of this new technology, and it's a new tool, right? It's unfamiliar. Most engineers have never heard of this kind of thing, and the ones that have remember it as a Gomez thing, which was a fail. So there's some baggage here that says no one would do it this way. Well, actually, I think that there is a place for this in the toolkit of a professional performance engineer. I'm not going to argue that every test, every performance test, every load test should be done this way, but I will argue that once in a while, a test like this should be done. So you catch that problem of the users are complaining and the performance engineers don't know why. Here's a slide that we developed. I developed it with the feedback from the LinkedIn community. But when and where do you provision your load generators? Some people were saying, I provision them in the same data center as the system under test. In fact, some people were saying, sometimes I put my load generators on the same machine as the system under test. Now, Paul Bruce said, no, don't do that, right? And boy, do I agree with Paul on that one. Don't do that. But there were some people who said, Yeah, no problem. We can do that as long as we watch for memory overruns and stuff like that. So some people said same data center as system under test, especially for B2B applications and regression tests, fast daily regression tests. Well, maybe that's acceptable. Or you could put it in a nearby data center. That was another popular answer. Where things got more interesting, from my point of view, was if once you got into a B2C application, now you're an app that's mobile traffic from all over the world, where you do care about the long miles and the last miles of the full distribution, then now that breaks into two cases in these two quadrants. For the frequent small unit regression tests, I would still accept that people want to use their multiple data centers or data centers for that because of the high repeatability. No problem there. But if you do that exclusively, if that's all that a performance engineer does, then that engineer is in the situation I described in the first case of the biased optimization and the failed termination, terminating too early from the optimization loop. I think that there's value in doing occasionally these infrequent but large user experience tests that really do measure something closer to the actual user experience worldwide. I'm noticing in the various discussions, including Arthur's was a very good example, Arthur and Stein's question that went with it. Agile DevOps methodologies seem to be putting an intense pressure in the last few years on schedules, reducing the budgets of the teams. Right? The performance engineers are being squeezed on how much time they have. Their jobs are being shifted out to other people and shared with other, small slices to other people who don't have the background and training. All of this is squeezing out the ability to actually do the performance engineering job well. All of this is putting a strong focus on the small daily regression tests, the automated regression tests that are really looking for a bad check-in from the development team. Like we're being reduced to being a cop on the nightly build. That's a crude oversimplification, but I see elements of that. Now my question is, who actually measures the response times at the end user locations in a broad way, measures the full distribution, not just a small number here and there, measures a real distribution? It is much worse than the nearby data center would suggest it is, and no one on the team is ever actually measuring that full distribution. If they aren't, then no one will ever know how bad the end user experience is, and then you get Stein's slide. The test engineer, everything looks good. The end user, this application, help, this application is too slow. There is a competitive advantage to be had for performance engineers who seize the opportunity and incorporate this kind of new technology into their toolkit for this important type of test, which now allows, for the first time now in over a decade, allows real optimization of the end user experience. Thank you very much. That's my talk, and I'd love to take some questions.
So first of all, thank you for this presentation. It was really interesting. And then you mentioned that your application test was hosted in Phoenix, and I was saying why all those people in Russia has bad response time. But now I got it.
Yes, that's the point. Just a straight line distance, it's a lot longer. It's about a second longer once you have the HTTPS handshaking. Then it really is longer. It's not just a 0.2 of a second. When you triple these delays, they start looking. Pretty soon you're talking real time here. Yeah.
Usually, yeah, I understand. I agree with you. I agree. So, Stein, I mean, have you noticed a lot of references to the raw data and all the things that you have been presenting over the years?
Yeah.
Yeah, no, that's great. No, the last mile, it's I also refer to it as the web performance assessments. And it is important, is what, if you talk about performance, primary measurement, response time, it's the last mile. It's
not just the last mile though. It's the whole
what
mile
counts.
all the way out to Russia, as well as the last mile to the So
yeah, indeed. It's really what counts.
Names that he called that the full mile.
Mm-hmm.
The whole mile or something like that. But yeah, there's the last mile part, and then there's the whole path. I'd call it the whole path. It's the many hole paths that are actually the dominant effect. The last mile is a little sweetener on top of that.
Because I totally agree with lots of performance engineers. That's not part of a job. It's the back end.
There's a lot of people that think testing tools, whatever angle you want on it, oh, it's not accurate, therefore you can't trust any of them, and let's just not test. Like, there's a lot of people that are like, let's just do whatever testing we can do, and those measurement things aren't accurate anyway. They're just a ball. I've heard so many rationales and excuses and whatever, and fewer and fewer people are like, well, let me do a network trace, and oh, look, there it is. I mean, it's plain as day. It's a special skill,
right,
potentially to be at that level, and having access to that level is sometimes hard for folks who are living in the container world. I was talking about that before. So I think this is great and excellent research, by the way, in looking at the different stacks. I did want to ask one question around sort of the Lotus stuff, because they roll a totally different stack the way they do their stuff. It's kind of a different ballgame. Do they run into some similar things, or is that do you see something similar happening with HTTPS?
Sorry, you said Lotus or Locust?
Sorry, did I say Lotus?
I think you said Lotus, but that's what I heard. What did you say? What did you mean?
The thing you do sitting on the kitchen table when you're on the weekend? The Lotus position, isn't that?
Lotus position. You do that on the kitchen table?
I think you do.
That's cool.
And everyone.
Yeah, me too.
No,
so what were you trying to say, Mark? Where were we?
Sorry. I was asking a little bit about your experience. I think you mentioned Locust, which is a Python-based, and they roll their own, they have their own stack, right, from a network perspective, different than the other things you would see in JMeter from a Java, HTTP, or Apache client, or the Java. And I think it was excellent you went into that. Yeah. I have not lived, I follow Corey Goldberg in the Locust world. Yeah. And there's some really interesting, compelling things. Did you see, is there more to share around what you saw with Locust, how it does this differently?
Sure. Well, sure. So you did see the plot. I had Locust, the Locust plot. Sure, I could bring that back up again, but it behaved different than all of the others. It was pretty strange what it did, right? It looked, JMeter had the periodicity. K6 had the super fine periodicity that got tippy as it went on, right?
Yeah.
And then that was K6. And then Locust had the skinny scallops,
right?
Some of which tipped and others of which stayed vertical, and they got dispersive as they went on. It was a triple difference. Locust was weird and different than all of the others. I looked at that one, what the hell is that? Right? Yeah. And I don't know. I'd love to get an explanation.
Join their Slack team. There's a couple of the inventors that are using that Python network interface set, and they've done some changes over the years that actually influence how that is used. So it's really an interesting, different than one virtual user equals one thread equals one channel equals one connectivity world. It's very different the way they have a low overhead piece, and they reuse it. They have a thread that bounces around between connections.
Well, that would probably explain this. Some of them are straight and some of them are tippy, and it's changing over time. There's a thread that's varying. It's jumping around. That would explain it. This is Mark. This is just great. I would love to talk with any of those guys any of those people who could look at this data that we've collected and recognize what would be causing that. Now, I got close to that in the discussion with Nicole Stein. You had asked about that, and I was thrilled that Nicole van der Huysen jumped on and said, "Hey, I'm interested in that." But then it looks like what she had in mind was to duplicate the effect in her lab on her machines. And I sort of misunderstood. I thought she wanted to, she used the word replicate. And I thought, oh, she wants to replicate my experiment. Here's the recipe. Here's the tutorial. You can try it. But it looks like that was the opposite of what she wanted. She wanted to replicate it on her machine, but then she would have to replicate it with machines at different distances. And even if she doesn't do the whole list of points in between at all the distances that I had, she'd at least have to do two machines. do one in the Netherlands and one in Hawaii, and at least get 2 points. And show the period is longer in Hawaii and shorter in the Netherlands. And that would be the endpoints of these tipping scalars.
Yep.
So there's a way to do it, but I really hope that Nicole will do the experiment, confirm the effect, and then explain why is it slower in Hawaii. That'd be great to know.
For the infrastructure world, where a lot of us used to live in development and now we're living in the infrastructure world much more, people used to be really worried about making global hops around to do transactions. I got a data center and I got 8 data centers around the world. And they just it's so enticing to be like, you know what, the business value of building all these remote locations, forget it, I'm going to run everything out of Phoenix. Have a nice day. And so this exact situation, I think business value-wise is really interesting just for those guys that are like, it should work. Look at that latency is so low. I should be able to do whatever. And they're not thinking of application level traffic. So this was great. I really liked it.
Fantastic, Mark. Thanks so much. Well, if there's any way that we could work together to develop a use case, or give you a free account, let you try it. I mean, that's what I really need is professional engineers to try it, see for yourself how easy it is to use, and begin using it really in your work. That's look, save money, get a better result. Make your company more competitive. What's not to like about that?
Yeah, it's great.
Thanks, Mark.
Thanks so much for your time, for building the slides, and welcome on board for the PAC community.
Fantastic. Thank you so much.